Your phone just survived a war. It fell off a table. It bounced. It skidded across the floor. And it's fine. Now imagine dropping that same phone onto carpet and the screen shatters. Carpet. The softest surface in your house. Killed your phone. Why? And that question is actually one of the deepest questions in all of materials science. And we're going to answer it today. But to get there, we have to start somewhere much smaller. Like atom level small. Here's the thing about materials. Every single thing you have ever touched, your chair, your shoes, your bones, the spoon you use to eat cereal at 2 a.m. is made of atoms bonded together. That's it. That's the whole game. The question is just, how are they bonded? And in what shape? Because that combination, bond type plus structure, determines literally everything. Whether something bends or snaps, whether it conducts electricity or blocks it, whether it survives a carpet drop or becomes expensive confetti. So let's start with bonds, because bonds are the personality of a material. You know how some people are super rigid, like they have one way of doing things and if you push them they just break? And some people are flexible, they bend, they adapt, they work with you? And atoms are the same way. It depends on who they're hanging out with. Metal atoms, for example, are basically the cool kids who share everything. They don't form bonds with a specific neighbor. Instead, all the metal atoms throw their outer electrons into one big communal electron cloud. Think of it like a mosh pit of electrons constantly moving around, and the positive metal ions just float in it. This is called metallic bonding, and it's why metals are ductile. They can be bent, stretched, hammered flat, because the atoms can slide past each other without breaking the bond. The electron cloud just moves with them. Now compare that to something like table salt. Sodium gives an electron to chlorine, chlorine holds onto it, and now they're locked into place by electrical attraction. That's ionic bonding. It's strong. It's rigid. But if you hit it at just the right angle, the layers shift. Suddenly you've got negative charges facing negative charges, and the whole thing repels itself apart. Shatter. Done. And then there's covalent bonding. Atoms sharing electrons directly with specific neighbors. This is how carbon bonds to itself in a diamond. And here's where things get actually insane. Wow. Carbon. One element. One type of atom. And depending purely on how those atoms bond and arrange themselves, you get either the hardest natural material on Earth or one of the softest, graphite, the stuff in your pencil. Same atom. Completely different arrangement. Completely different material. Wait. Hold on. The same element, carbon, can be the hardest thing and also leave a smudge on paper. And yes. That's not a trick. That's materials science. In diamond, every carbon atom is bonded to 4 others in a tight 3-dimensional tetrahedral lattice. Every bond is pulling in every direction. Incredibly hard to deform. In graphite, the carbons form flat hexagonal sheets bonded strongly within the sheet, but the sheets are only held to each other by weak forces. So the sheets slide right off each other. That's why it writes. You're literally leaving layers of carbon on paper when you draw. So we've established that bond type and atomic structure are the fundamental code of a material. But here's the real question. Why does structure matter so much at the macroscopic level? Meaning, why does what's happening at the nanoscale decide whether your phone screen lives or dies? To answer that, we need to talk about what happens when you apply a stress to a material. When you push or pull on something, when you drop it, bend it, squeeze it, you're applying a force per unit area. That's stress. And the material responds by deforming. That deformation per unit length is called strain. And the ratio of stress to strain? That's the elastic modulus. Basically, how stiff is this thing? And now here's the key distinction. Elastic deformation is reversible. You push on a rubber band, it stretches, you let go, it comes back. The atoms moved, but the bonds didn't break. Plastic deformation is permanent. You bend a paperclip, it stays bent. The atoms actually shifted into new positions. And fracture is when the bonds break outright. Things fall apart. Screen goes crunch. Your phone screen is glass. And glass has no mechanism for plastic deformation. None. There's nowhere for the stress to go. It can't bend. It can only store elastic energy right up until the moment it can't, and then it releases all of that stored energy at once, in a crack. That's not bad engineering. That's just what an amorphous, covalently bonded material does under impact. The carpet drop is actually worse than a hard floor in certain cases, because the carpet deforms slowly, concentrating the impact rather than letting it spread. Now you see it coming, don't you? N. We've got the atomic scale, we've got the bond scale, and now it's time to go up a level. Because materials science isn't just about individual atoms. It's about what happens when you have trillions of them, arranged in specific patterns, with specific defects, in specific phases. And that's where it gets genuinely weird. Let's talk about crystals. And no, not the kind your aunt puts on her windowsill to heal her chakras. Nah, real crystals. Because almost every metal you've ever seen, the steel in a car, the aluminum in a soda can, the copper in a wire, is crystalline. That means the atoms are arranged in a repeating, ordered lattice. Like a 3D grid, going in all directions, billions of times over. And this structure is why metals behave the way they do. But here's the twist. It's not the perfect structure that makes metals useful. It's the imperfections. Hear me out. Imagine a perfectly stacked brick wall. Every brick exactly in place. You push on it, it pushes back rigidly. Now imagine the same wall, but one brick is slightly off. Maybe it's a different size, maybe it's just shifted a little. Now when you apply a force, the stress concentrates at that misfit brick, and the wall can actually accommodate the deformation by moving that irregularity through the structure. That irregularity is called a dislocation. And dislocations are why metals can bend without shattering. When you push on a metal, dislocations move through the crystal lattice. They're like ripples. They allow planes of atoms to slide past each other without breaking all the bonds simultaneously. Just one bond breaks at a time, then the next, like unzipping a zipper. That's plastic deformation at the atomic level. That's why you can hammer steel into a sword, bend a copper pipe, or crush an aluminum can without it exploding. Now here's the actually insane part. Wow. Steel is iron with a tiny bit of carbon in it, usually less than 2% by weight. That's it. And yet steel is dramatically stronger than pure iron. Why? Because those carbon atoms wedge themselves into the iron lattice and pin the dislocations. They physically block the movement that allows deformation. Fewer dislocations moving means more stress required to deform the material. More stress required means stronger material. The entire global construction industry, skyscrapers, bridges, cars, ships, runs on this one trick. A little bit of carbon jamming up atomic traffic. This is the midpoint. Stop for a second. Because this is genuinely mind-blowing if you let it land. The Eiffel Tower. The Golden Gate Bridge. Every skyscraper you've ever seen in a city. All of it, stands up because tiny carbon atoms, invisible to any naked eye, are sitting in iron lattices blocking the movement of defects that you could never see either. The macroscopic world, the world of skylines and suspension bridges, is being held up by a game happening at the scale of individual atoms. We didn't even know atoms existed when we started using steel. We just discovered empirically that if you add carbon, iron gets better. The atomic explanation came centuries later. That's material science. The world was using it before we understood it. Okay, back to building upward. We've talked about metals and crystals. But what about things that aren't crystalline? Glass is the big example. Glass is amorphous. The atoms have short-range order, meaning nearby atoms have a regular arrangement, but there's no long-range repeating lattice. It's more like a frozen liquid than a true solid. And because there's no crystal lattice, there are no dislocations. There is no mechanism to redistribute stress gradually. So when a crack starts in glass, it propagates at terrifying speed, we're talking kilometers per second, because every atom in the crack path is bonded directly to the next, with nothing to slow it down. Now let's bring in a completely different class of materials. Polymers. You know them as plastic, rubber, nylon, Kevlar. The stuff your water bottle is made of, your hoodie, the tires on a car. Polymers are long chain molecules, thousands or millions of atoms strung together in sequences. And the behavior of a polymer depends almost entirely on how those chains interact with each other. If the chains are loosely tangled, like a pile of cooked spaghetti, you get a flexible polymer. The chains can slide past each other. That's your plastic bag. If the chains are cross-linked, meaning they're chemically bonded to each other at intervals, you get a rubber-like network that can stretch but snaps back. That's elasticity without crystallinity. And if the chains are perfectly aligned in a regular pattern, you get something like Kevlar, where the molecular structure is essentially acting like a crystal, which is why it's stiff enough to stop a bullet. Here's the beautiful unifying pattern. Whether you're talking about metals, ceramics, glass, or polymers, the game is always the same. What are the bonds? N. What is the structure? N. And how does that structure respond to energy being put into it? N. It's the same question at every level. And now, because we've gone from atoms to metals to glass to polymers, we're finally ready to talk about the stuff that made the modern world possible. The stuff that's in literally every electronic device you've ever touched. Semiconductors and superconductors. And why one of them is about to change everything. Silicon. You've heard the name. Silicon Valley. Silicone implants. Wait, those are different. That's a polymer. Don't get confused. Silicon, the element, is a semiconductor, which means it conducts electricity. But only sometimes. And that sounds like a flaw. It is actually the most useful thing in the history of human civilization. Here's why. Metals conduct electricity because of that free electron cloud we talked about. Electrons move easily. Current flows. Insulators, like rubber or glass, have electrons locked tightly into bonds with no freedom to move. But silicon sits in the middle. Its electrons are bound, but not impossibly so. If you add just a little energy, a small voltage, a photon of light, you can knock electrons loose and make silicon conduct. You can turn it on and off. And off is the binary language of every computer ever made. But here's the actual magic trick. You can tune silicon's conductivity by doping it. That means deliberately adding tiny amounts of other atoms, phosphorus, which has an extra electron, or boron, which has one fewer. These dopant atoms change the electron balance, creating either extra free electrons or extra holes, which are basically absences of electrons that act like positive charge carriers. Put an N-type region next to a P-type region, and you've built a PN junction. That junction is a diode. 2 junctions is a transistor. Stack billions of transistors on a chip the size of your thumbnail, and you've got a processor. That's the entire digital revolution. All from controlled impurities in a crystal. And now the comparison that hits like a plot twist. Remember how we said that adding carbon to iron pins the dislocations and makes steel stronger? We added impurities to control mechanical behavior. Now we're adding impurities to silicon to control electrical behavior. Different material. Different scale. Different industry. Exact same conceptual trick. Control the defect. Control the property. This is materials science in its purest form. Now let's go one level weirder. Superconductors. In a normal conductor, electrons moving through the lattice bump into atoms, and that friction generates heat. That's resistance. That's why your laptop charger gets warm. It's energy being wasted. In a superconductor, below a critical temperature, something quantum mechanical happens. Wow. Electrons pair up, called Cooper pairs, and they move through the lattice in a coordinated quantum state, where they essentially stop interacting with it. Zero resistance. Literally zero. Not very low. Zero. What does that mean practically? It means a current you start in a superconducting loop will keep flowing forever. No battery. No energy input. Just circulating current indefinitely. And superconductors expel magnetic fields completely, which is why a superconducting magnet can levitate things above it. The MRI machine in a hospital? Superconducting magnets. The particle accelerator at CERN? Superconducting magnets. This is real technology being used right now. But the catch is that most known superconductors only work at temperatures close to absolute zero. We're talking minus 269 degrees Celsius. That's colder than outer space. Cooling something to that temperature costs enormous amounts of energy and money. A room temperature superconductor, one that does this at ordinary conditions, would be one of the most transformative discoveries in human history. Lossless power transmission, maglev trains everywhere. Computing architectures we can barely imagine. And we don't have one yet. There have been claims. In 2023, a paper announced a room temperature superconductor called LK99. The internet lost its mind for approximately 1 week before independent labs couldn't reproduce it. The discovery turned out to be a measurement artifact. But the fact that the world reacted that way, scientists dropping everything, labs racing to confirm, tells you exactly how much is riding on this question. So let's zoom all the way back out. We started with a shattered phone screen on carpet. We went down to atomic bonds, then up to crystal lattices, dislocations, steel glass, polymers, semiconductors, and now superconductors. And the thread running through every single one of these is the same. Structure determines properties. The way atoms are arranged and how they're bonded dictates every behavior of the material at human scale. That's the whole field. Everything else is details, beautiful, world-changing details, but details. The Nokia 3310 meme exists because that phone genuinely felt indestructible. And it was, by the standards of its time, because it was a thick chunk of polycarbonate plastic with cross-linked polymer chains and no brittle glass screen to shatter. It was materials, science. Mundane materials science. Done right. Your modern smartphone is also materials science. Thinner, lighter, faster, more powerful, and also, yeah, more fragile. That's not a mistake. It's a trade-off. Every material decision is a trade-off. Strength versus flexibility. Conductivity versus insulation. Hardness versus toughness. Weight versus stiffness. You don't get everything. You choose what matters. And somewhere out there, right now, a materials scientist is looking at a crystal structure on a computer screen, trying to find an arrangement of atoms that breaks all the trade-offs at once. Trying to build something that doesn't exist yet. Something harder, lighter, more conductive, and stable at room temperature. We're still building the table of possible materials. We don't even know how big it is.